I think, Arun sir, we can start now. So,
Okay,
hand
sir.
over to you.
So a very good afternoon to one and all present here, of course, online. A very warm welcome to this second session on second day of this FDP on recent advances in computer science and allied domains. Heartiest welcome to our guest and speaker, who is none other than Dr. Swagatam Das. Hope you all are enjoying the sessions and learning a lot. Believe me, how difficult it is to introduce a person like Swagatam Das in a few minutes. He is such an eminent personality. Even then, I'll try my level best to introduce him to the audience. Dr. Swagatam Das received his BE in Telecommunication Engineering as well as ME in Telecommunication Engineering with specialization in Control Engineering and PhD degrees all from Jadavpur University, India in 2003, 2005 and 2009 respectively. Swagatam Das is currently working as an associate professor at the Electronics and Communication Sciences Unit of the Indian Statistical Institute, Kolkata, India. His research interests include evolutionary computing, pattern recognition, multi-agent systems, and wireless communication. Dr. Das has published more than 300 research articles in peer-reviewed journals and international conferences of review. He is the founding co-editor-in-chief of Swarm and Evolutionary Computation, an international journal from elsewhere. He has also served as or is serving as the associate editor of the Pattern Recognition, published by elsewhere, and Neurocomputing, again from elsewhere, Information Sciences, elsewhere, IEEE Transactions on Systems, Men and Cybernetics Systems, IEEE Computational Intelligence Magazine, IEEE Access, and so on. He is an editorial board member of Progress in Artificial Intelligence by Springer, Applied Soft Computing by Springer, Engineering Applications of Artificial Intelligence by Springer, and Artificial Intelligence Review by Springer. Dr. Das has 19,900 plus and 19,911 to be exact Google Scholar citations and an H index of 65 till date. He has been associated with the international program committees and organizing committees of several regular international conferences, including IEEE CEC, IEEE SSCI, SEAL, GECKO, and SEMCO. He has acted as guest editors for special issues in journals like IEEE Transactions on Evolutionary Computation and IEEE Transactions on SMC Part C. He is the recipient of the 2012 Young Engineer Award from the Indian National Academy of Engineering. He is also the recipient of the 2015 Thomson Reuters Research Excellence India Citation Award as the highest cited researcher from India in engineering and computer science category between 2012 to 2010 to 2014. And I was fortunate enough to see him receiving this award in that event, as me and Dr. Ankur were also attending that event. In fact, he has received so many awards and recognitions that it is not possible for me to mention each one of them in such a short span of time. For this, my dear friends, you need to visit his cyber home, where you can find a lot of information about him. And with this, may I now invite Dr. Das to kindly take over and address the audience. Today, he is going to speak on an introduction to deep machine learning. And Dr. Das, just let me also introduce the audience to you. In the audience, we have research scholars, PG students, faculty from various universities across India and abroad, and as well as we have some UG students, plus the software professionals working in software industry. So this is what we have in audience. So Dr. Das, may I request you now to kindly take over?
Thank you very much, Professor Arun Prakash and Professor Ankur Chaudhary.
Welcome, sir.
Firstly, for inviting me to this session and then for this warm introduction. I would like to share my screen and start the lecture.
Sure, sir.
With my slides. And So please, you can, anytime you can ask me questions as soon as you don't understand anything, or as soon as you are not able to hear my voice or something technical comes up.
So usually what we are doing, that we are doing question answer session at the end, because we have not allowed the participants to unmute themselves. So what we will do, we will ask the participants to type their questions in the chat section. And then later on after the session, I will read the questions for the audience to use it.
Sure, that's much better. But if at the point, at any point of time you cannot hear my voice or you cannot see the slides, please immediately let me know.
Yeah, sure, sir. Sure.
Fantastic. Okay. So, as many of us know, deep learning, this word has become almost ubiquitous to almost all disciplines of science and technology by this time. And for last 4-5 years, machine learning is almost everywhere. In fact, the job market for people who are completing their bachelor's degree in engineering or master's degree in computer sciences or related areas, the job market has become more or less driven by knowledge in data analytics and machine learning. And this boom of analytics, the boom of all these terms which have almost entered into our drawing room, like big data, machine learning, data analytics, these terms have almost become a household terms rather than research jargon, because of the huge research impetus that has been developed by people in deep learning. So I think, although this workshop is more or less general, and I assume many participants are from diversified backgrounds, still it will be good enough for them to have somewhat an exposure to deep learning. Obviously, this talk is not exactly meant for the deep experts of deep learning. This talk is not exactly meant for them, but it should give everyone horizontal exposure to this very rapidly developing field. So we start with a very basic question of what is meant by machine learning. So there are two terms if you look at this term. One is machine and one is learning. By machine, we obviously mean computers, which can be programmed, but which can be provided with a sequential set of instructions to carry forward some given task. On the other hand, by learning, this term learning is a very interesting term. You know, what do we exactly mean by a learning system? Okay. By learning system, we mean a system which can take correct future decisions based on the past experience provided to the system. This is very interesting. I mean, what is meant by taking a correct future decision and what is meant by based on past experience? Not only that, these systems actually improve this capability of taking a future decision with more and more past experiences given to it, right? So let's see what is meant by these terms very naively. When I was a kid, or all of you were kids at the age of 3-4 years, to teach me, this must be common to many of you. The mother used to teach us about, say, animals around us by pointing into a kid's storybook, picture book, and saying, look, this is a cat. She points to a printed cat's picture. This is a dog. This is a rat. That is something else, fox. So after a few rounds of some such training, when we go on road and a creature passes by me, I would yell out, mother, look, that's a cat which passed by me. Or that's a dog which passed by me. So what did I exactly do? My mother was pointing to a picture repeatedly and telling me, this is a dog, this is a dog. Somehow, the gross shape, texture, size of that particular animal was registered here in my brain, or in my, I would say, neural circuit, biological neural circuit, under the tag word of dog. And when the small creature on road passed by me, although the exact appearance of that creature was not same as the one printed in my book, I would still somehow match it. And I would say, mother, look, that's a dog. So what I did is I took a future decision. I took a decision in some circumstances based on the experience which was given to me by my mother. And this is common to all kids, all human kids. Everyone starts learning like this. So this is a form of, learning, which we say in terms of computer science, which we call supervised learning. So mother is like the teacher or supervisor who is giving a name to some specific group of objects. And in my brain, I could immediately see such an object and match with those previous objects. Okay. So with more and more, experience coming in, this capacity of taking the right decision also improves. This is very interesting. What does it mean? I was a fan of, Bollywood singers, playback singers, lady singers. So when I was 19 years of age and I would listen to a Hindi film song sung by a woman, I would yell out, mother, see, Lata Mangeshkar is singing. I was a fan of Lataji. In my family, everyone were. So any female singer sings, I would say, mother, looks, Lata Mangeshkar is singing. I could not distinguish. But as my age grows, when I was 14, 15, and I actually heard many more songs sung by different, lady playback singers, then I was able to clearly distinguish between Lata Mangeshkar, Asha Bhosle, Kavita Krishnamurti, Sunidhi Chauhan, and so on. So I could clearly listen to a female voice and immediately say who was singing. Is that clear? Now, if someone asks me, write a paragraph on how you can distinguish between Lata Mangeshkar's voice and Kavita Krishnamurti's voice, probably I won't be able to do that. Nobody of us can do that, isn't it? So this knowledge cannot be directly transferred into the written form or into an explicit form. This is very interesting. So this is what happens. Sometimes the knowledge is not directly transferable, but we do that. This is where machine learning starts coming in. The term was coined in 1959 by Arthur Samuel, as you can see. And this slide actually tells you what is the difference from traditional programming. In traditional programming, you are given some data and some program. Those who do computer programming at least must know this much. So in traditional programming, what we do is we provide to the computer some data and some program. What is this program, by the way? This program is basically a sequence of written instructions which must be, executed step by step by the computer to carry out some specific task. Like your computer is provided with lists of numbers and maybe lists of integers and maybe a program to sort these integers in ascending or descending order. There are so many, sorting algorithms out there, bubble sort, quick sort, merge sort, etc. And the computer executes those instructions step by step inside the program on the data and gives you some output. On the other hand, this is traditional programming. The goal of machine learning is, as if you look at the lower one, you will provide the data to the computer, some kind of raw data. You will also provide some kind of, expected output or target output to the computer. So you will provide raw data and you will provide target output to your computer. The computer must tell you how you can generate such output from the data. That means the computer needs to learn a way of generating such output from the data. That means the computer needs to write the program by its own self. Then we say the computer becomes intelligent and the computer is actually learning to do something. So in that circumstances, I will provide the computer with, lists of numbers, many lists, 5, 6 such list of numbers. And I will also provide the computer with the ordered numbers, sorted numbers list. And the computer has to figure out how to sort these integer lists so that many constraints like number of arithmetic operations should be a minimal. Okay, the operations must not take huge amount of time, etc. So obeying all such constraints, the computer must figure out a good sorting algorithm. That is the idea, that is a dream of machine learning. Let the computers program by themselves. We are not going to write them program. That is one of the biggest dreams achievable by the artificial intelligence community in general and machine learning community in particular. Okay. So the supervised machine learning framework on which we will mostly, focus, the entire business can be expressed in the form of this simple mathematical equation, y equal to fx. So we call it x is a particular vector of numbers, x is some kind of numbers, which is processed inside a system. This system is your learning system or learner. In statistics, we call it prediction function. And the final output is another kind of numbers or another kind of, better I say, vectors or even matrices maybe, which is for the output from this prediction function. So the whole domain can be expressed in terms of this simple mathematical function, y equal to fx. Usually, x is the, when we talk about deep learning, we will confine ourselves to, images and videos, etc. But it can be anything else. So given a training set of labeled examples, these training sets are, classified as x1, y1, x2, y2 up to xn, yn, where each x1 bar or this x1 bold is a vector comprising of, features of the objects that we want to categorize, about which we want to take a decision, about whose category we want to take a decision. And y1, y2 up to yn, these are the tags or class labels. Just like when the computer has to recognize certain different animals, the computer first must be shown with the pictures of some dogs, gross appearing dogs, cats, rats, etc. And the features of a dog image are listed in the form of x1 bar. So if we say this x1 is basically the features of one particular image of a dog, y1 is the tag named dog, that this image belongs to the dog category. x2 may be containing the features of another another dog image, and y2 is basically the tag board that this is another dog, and so on. So for those who are very new to this area, let me tell you, at first, every object about which you want to take a decision, to which category this object belongs. If you want to take a decision like that about every object that you want to do this, you first must, convert the description of the object in terms of suitable number format into some related numbers, which together create a feature vector. So this process of converting objects into numbers is very common. Even the science community is doing this even before the advent of computers. For example, in physics, when we have a gas-filled container fitted with a piston, we very frequently describe it in terms of three numbers, which are the pressure, volume, and temperature. Okay, and we actually, depict that gas-filled container in terms of these three numbers in the thermodynamic state space. The first ever data set, machine learning works on data. So the first ever data set that was scientifically documented for the study of statistics is called the iris dataset, which contains 150 iris flowers collected by biologists. And these iris is a flower just like our rose. And there are three scientific categories of iris flowers, as many of you may already know: Iris setosa, Iris virginicea, and Iris veriscala. So the scientists, biologists, took 50 samples from each class, and then they converted each flower into 4 numbers. These 4 numbers were floating point numbers. They were not integers. What are these numbers? These were, every flower has a petal and a sepal. So these 4 numbers were the sepal length, the sepal width, the petal length, and the petal width. Okay. And every iris flower was expressed in terms of one of these 4 numbers. Now, the supervised learning problem is, suppose I provide these 150 iris flowers to a computer. Try to understand. Each flower has now become a vector of 4 numbers: petal length, petal width, sepal length, and sepal width. Computer doesn't understand a flower by its appearance, fragrance, color, etc. Computer understands only numbers. Better I say basically binary numbers. So now I provide these 4 numbers for each flower to the computer, and I also provide a class label. Class label means whether it is veriscala or virginicea, etc. So what I give to the computer is an ordered pair in terms of mathematics, which can be expressed in terms of x1 bar y1, x2 bar y2, x3 bar y3, and so on. Each of these x contains 4 numbers corresponding to the 4 features of the flower, and y is basically the class label, which can be another integer. If I stamp these 3 classes as 0, 1, 2, then y can be either 0 or 1 or 2. So I provide the computer with these 150 ordered pairs, and a new flower comes. How many iris flowers can be there? Infinitely many. How much I am showing to the computer? Only 150. So I am showing the computer 150 stamped iris flowers. Now a new iris flower comes. I must provide its 4 numbers, 4 features to the computer, and the computer must tell me what is its correct class, to which class between this Iris veriscala or virginicea or setosa
Sir,
this
Swagatam sir.
flower belongs.
Swagatam sir, may I interrupt you for a moment?
Hello?
Yeah. Sir, your slide, I think, has got frozen at this supervised machine learning framework.
Oh, okay. Let me reshare it.
Yeah.
Can you see it right now?
It's the same one, sir. Supervised machine learning framework. I think it was the second slide only. Yeah.
Is it changing right now?
Yeah, it's changing now. It's changing now.
Okay. So this is the new slide actually I was talking about. So
Sure,
this,
sir.
every object that you want to categorize must be converted into a group of numbers, which we call feature vector. That feature vector goes inside this function. The function accepts the feature vector, and the function must output what is the correct class label for this particular feature vector. So here in this slide, we are representing feature vectors just as an illustrative purpose by these images. Now from images, various types of features can be extracted. There is, decades-old research efforts on this. So as I was telling you, the supervised learning problem, if I just go back to the previous slide only, the supervised learning problem is you will give your computer 150 such ordered pairs for the iris recognition problem, classification problem. And the computer must estimate this function. The whole business is in estimating this function y equal to fx. When a new flower comes, a new x comes, depending on this function, we will infer its class level. This is the whole business, machine learning. So steps in supervised learning are, first, you have a bunch of samples or example images from each class. Like here, we have number of apples, different types of apples. Even if you want to, learn the apple class, your apple class may contain green apple, yellow apple, fully ripe red apple, and so on. This is intra-class variance. Similarly, you have various shapes of tomatoes, pears, etc., puppies. So you take these training images, you extract the correct image features from each of these training images. Now, images can be described in terms of pixels or textures or wavelet coefficients or Gabor filter coefficients. There are various methods of representing each image in terms of suitable numbers. And these various methods have been engineered by human researchers for last 40, 50 years and mostly practiced under the area of computer vision and image processing. The whole sect of research in computer vision was dedicated on how to represent each image in terms of suitable numbers, which can correctly characterize, the features of each image. These are image features. Now, there is some human expert who will assign correct labels to these images. This human expert was like my mother in my example, when she was pointing to different creatures, images and saying this is a cat, this is a dog. Similarly, there should be a human expert who will assign suitable training labels to each image. Okay. Then the process of training means the process of creating the function y equal to fx. Once this function is created, this prediction function is also called the learned model, the supervised learner, the machine learning system, and blah, blah, blah. There are various names for the same thing. We can call it model or system, whatever. So once this model is learned, next a new image comes, which was not included in our training set. So we will extract the image features from the new image, and we will pass these extracted features through the learned model, and then we will see what particular category is inferred or decided for this new image by our learned model. Then we say, yes, this is the image of an apple, or this is the image belonging to the pears class, or this is the image of tomato, etc. This is the whole business of machine learning, or better I say, supervised learning. Okay. So now, just can you? Is there a problem in hearing me, or can you still hear me clearly?
No, it's fine. It's fine, sir.
Thank you. Okay. So now, why this business is very hard? To human beings, why this is very hard? If you look at this image, as human being, we clearly see it's a motorcycle. So we immediately, by looking at an image, actually our neural networks inside the brain perform lots of computations, but those computations appear so quickly that they are almost invisible from us. So we immediately look at an image and we immediately decide its category. Oh, it's a motorcycle. But what does the machine sees? When we look at an image like this, the machine sees the camera. Machine means here a camera. The camera sees an array of numbers. And these numbers are basically the intensity or brightness value of each point. If it is a color image, the camera will see three such matrices of numbers in the red, green, and blue, shade. From these piles of numbers, it is not very, straightforward to infer about the category of this particular object. This is where from the problem in traditional machine learning starts. It is not easy. If you are, instead of a real picture, if a human being is provided with an array of numbers, the human being can never tell what is hidden inside the array, whether it's a big motorcycle or it's a hippopotamus or what it is. We cannot say, right? So we see this, the camera, the machine sees this array of numbers. So now, how can we, let's say, okay, when the camera grabs an image, when the camera clicks an image, it basically records such brightness of different points on the image in terms of, integer, and it records them in a matrix styled data structure, stores it as a digital image. Now, these pixels are, we call them the lowest level features. They are very close to the machine. They are the lowest level features which can represent an image. They are not close to human beings. Each image is represented in the form of brightness values or gray level intensities or color intensities. But these intensities are not close to the human beings. Because this is much like, when you write a program in C or C++, and when you try to execute the program is ultimately converted into an executable code, .exe file. We say that executable code, nobody can understand that executable code except a computer. So we say that executable code is a low-level representation of your program. It is very close to the computer. And the language in which you actually wrote your program, that is a high-level language because that is close to the human being. Similarly, images should also have some high-level descriptions based on which human beings interpret and understand images. When you see the face of your friend, you don't say, okay, the top left corner has a pixel intensity of 212, beside this 194, below that 64. No. You basically look at whether the person has a wide forehead, very thick mustache, nice beard, cut mark on chin. These are the high-level descriptions based on which we usually look and remember faces. We don't remember faces in terms of numbers. And the ultimate quest of neural networks or machine learning research was ultimately, can we make a computer similarly understand images in terms of high-level descriptions, not in terms of pixels? This is the quest from which deep learning actually grew. Okay. Now, usually how we represent images. If you tell me, what we could do is, suppose I want a two-dimensional representation of an image. So I could simply merely pick up 2 pixel values from 2 random locations and plot 1 pixel value along x-axis and the other pixel value along y-axis. As a result of this, for many different images, even these 2 pixel values will not have any regular correlation, as a result of which pixels sampled like this from card images as well as non-card images will have a mutually intertwined, scattered, and bad representation. If your job is to, segregate card images from non-card images, suppose you want to design a surveillance camera to be mounted on the gate of your garage, and you want only cars to enter your garage, not an elephant, then you have to distinguish cars from non-cars like elephants, zebras, giraffes, etc. So what will happen if you just take 2 pixels from the image and you represent each image as a dot in this 2-dimensional space? What is happening? What the stupid thing is happening is both card and non-card images are becoming intermixed. You cannot actually distinguish them. So you cannot alert everyone when an elephant is, entering into your garage. So as a result of that, what better thing we could have done is, we could have rather take 2 small windows. Each window is a 3x3 matrix or 5x5 matrix. We could have slide these 2 windows on the images And as soon as one of these windows captures a handle-like structure, it will provide a very high response or a very high number. These windows actually evaluate the 9 pixels or the 25 pixels that they capture. So each window is a 3x3 submatrix. It captures 9 pixels from your image, and it actually does some kind of processing on those 9 pixels. Such windows are usually called feature detectors. I will come to it. So when the feature detector is able to catch a handle, it will record a very high response. Similarly, when the other feature detector captures a wheel, circulars with spokes and so on, it will also register a very high response. If I plot the response of the feature detectors along the X and Y axis, along the X and Y direction, then the response provided by the cars will be towards this higher end, higher values of along both X and Y axis. On the other hand, the response provided by the non-cars will be more towards nearer to the origin, and you should be able to distinguish between them. So see, proper representation of the numbers based on which you are going to characterize each of your objects plays the most important role. If you cannot represent your object suitably in terms of the rightmost numbers, you will fail to organize them correctly into different classes and to infer various categories for each of these objects, etc. And these days, we have so intricate imaging devices that our challenges are even much, much more. For example, classification between only 2 classes. If you look at these images and try to see, I mean, as a human being, you can still tell us what is what, which one is a KFC chicken and which one is a Labradoodle, a small puppy of the Labrador quality. You can still tell us. But since the textures are very similar, for a computer to do this classification may not be that easy. And not only that, as a human being, you can easily recognize based on which feature you are doing this. Can you tell me based on which feature you are doing this? First interesting feature might be the presence of the 3 dots for the Labradoodle, which tell us, 3 dots for the Labradoodle, which tells us, the 2 eyes and 1 nose. Okay. Similarly, we can have this set of pictures which captures both a barn owl and an apple. So the apple has 2 seeds and the barn owl has 2 eyes. But as a human being, if you look at the distance among these 2 eyes, you see that's much more than the distance between the 2 seeds. So by looking at these intricacies, you can infer which one is barn owl and which one is apple. Similarly here, this one is probably the hardest one. Okay, chihuahua or muffin. We have these muffin cakes with cherries and also chihuahua. Still, we can have multiple muffins and multiple chihuahua. These are mostly the hardest data sets towards any traditional computer vision system. So if you provide this image to a computer vision system and ask it to distinguish, many times it can fail. As human beings, we can do that very easily because our visual system is it's a remarkable system. It is engineered by the Almighty God, so it is very mighty basically. So if you look at it, even you can recognize these eyes and nose, they are ordered uniformly as the vertices of almost a uniform triangle, unlike the cherries on the chihuahua, which are ordered mostly haphazardly. Okay. So our visual system is so improved that we not only distinguish, but we can also figure out the features based on which we are distinguishing, right? Not so easy for computers. So for over last few decades, as I told you, last 3-4 decades, there has been lot of research in image and video processing, computer vision communities, computer graphics, to capture the suitable features which can distinguish various images from each other. And this is called the human intervened feature engineering. Okay. And various, feature representation techniques have been devised, like this scale invariant feature transform, which is now a textbookish topic for computer vision, SIFT, HOG, histogram of oriented gradients, textons, RIFT, and so on. So a lot of it depends on proper feature representation. However, the tragedy is one particular type of feature representation may not be sufficient for other types of images. And there are various sort of images, that we want to deal every day. For example, the chest X-ray images, okay, CT images. So now from the chest X-ray images, if I want to segregate regular pneumonia traces versus the COVID-19 pneumonia traces, we need to have some, already stamped, already labeled images by the doctors. By using the expertise of some doctors, the doctor may label only 50 such images, 30 regular pneumonia, 20 COVID-19 patient. So based on such stamping, I have to take a new image, and the computer must tell me that new chest X-ray image, whether it's a COVID-19 positive person or it's a regular pneumonia patient. The pneumonia has nothing to do with COVID-19. Can I do that? This is the question that comes up. Now, the problem is, since most of these chest X-ray images do not have these regular, maybe SIFT, RIFT type of classical feature extraction techniques may not work best on new type of chest X-ray images or CT images. Techniques that work fine with satellite images or natural scene images may fail for different types of medical images. So there is always a no free lunch principle in this human intervened feature engineering. No free lunch means, no free lunch is a fundamental principle in machine learning, which means no one is offering you a lunch free of cost. If anyone does, that means that person is going to ask for some undue advantage. If you translate it in this scientific discipline, it means if one particular feature extraction method has distinct advantages in some particular type of images, be sure it will have very bad performances for some other type of image domain. So there is no single medicine which can cure all possible diseases. There is no single feature extraction technique, no one universal method which will work best for all types of images, videos, texts, everything that we want to categorize. Nothing, no such universal technique is there. And this is some problem, this is some inherent problem from where so this is something, yes, I know, I mean, chest X-ray may not be just, this is just an example that I gave you. CT images may be more stable, but the problem is CT images are even more costlier. I will come to a discussion of this later on. So the problem is this human intervened engineering, feature engineering is not always reliable and not always, the best for different general performance of machine learning systems. That is why. So that is why basically. So there are some questions in the chat. I will answer these questions later on, right?
Yeah, we will take the question answer session at the end, sir.
Yes. Once the session is over, we will take these questions. Right?
Sometimes what happens, most of the questions are answered during the discussion only. So we
Yeah,
will discuss the
fine.
questions later.
Okay. So continuing as further, this is why the machine learning community is so mad after deep learning. I hope many of you have seen this nice meme in coming years. So that's why researchers are all doing what nowadays the time has come when the traditional machine learning models have become almost obsolete, except for very small and well-defined data sets and very specified application areas. Otherwise, everyone is becoming mad after deep learning. Although deep learning is not magical, it's nothing like a magic, but still people are, because it offers some very distinct advantages. First, let us look at what are these distinct advantages. Then I will tell you why it is not a magic. Okay. So this is a very famous slide taken from this link given below. What does deep learning offers? In a traditional machine learning cycle, what we see is you give some input. There is a human feature extractor which extracts suitable features from the input and which provides these features to a classification system. So this human feature extractor must decide based on the type of the image whether he will extract, textures, or he will extract wavelet coefficients, or he will extract something else in the name of features. Then he will provide those features to a classifier, and the classifier will decide whether it is a car or it is a non-car or what is the category. Now, deep learning eliminates the need for this human feature extractor. A deep learning system is basically a cascaded connection of many simple systems. Cascade means input of the previous layer provides, output from the previous layer appears as the input to the next layer, and so on. So this cascaded system removes the need for human feature extractor. So the network itself decides the best suitable features based on which these objects must be represented given the specific domain of application. So we do not have to bother. We do not have to, think of the best feature set, or we do not have to think of the best feature transforms. We just provide the image in terms of the lowest level recorded features, that means pixels for an image, to the computer. The deep learning system itself makes many nonlinear transformations and combination of these pixels to generate the interpretable high-level features, which will best represent each object for the designated classification task. That is the idea of deep learning. This makes the classification very, very accurate and non-subjective. So this is just a hierarchy of how the deep learning systems can extract features. So starting with the pixels for a facial image database, it combines the pixels into edges into object parts like eyebrows, lips, nose, etc. And finally, object parts into abstract object models, based on which we determine whose face is this. Just like I told you at the very beginning of this talk, that the gross appearance shape of a particular kind of creature is stored in my brain under the tag word of dog. Similarly, each face, when I want to recognize the face of one of my 10 friends whose faces are stored in some face database, I have a prototype for each of these 10 faces. Although I have multiple images for each face, you can click your friend's face from different angles, different lighting conditions, and blah, blah. So each face is basically the face of the same person. So I have a prototype for that face stored in my brain. Such prototypes are actually learned starting from simple pixels in a deep network, deep learning system, or deep neural network. That is why this particular mode of learning is also called representation learning. It learns how to represent. Okay. Deep learning has a very rich history starting from 1940 and coming to, I mean, initially the first golden age of artificial intelligence and deep learning was probably between 1960 and 1970. And see how things happened. In 1970, in 1969 to be more precise, Minsky and Papert, they showed that a classical neural network, at that time it was the state-of-the-art artificial intelligence system, it cannot distinguish between objects if they are linearly non-separate. Like if you look at this XOR problem picture, the three black dots on one side of this line and the white dot on the other side, it's fine. A classical neural network can distinguish between them. At that time, there was only perceptrons mostly and Adeline neurons. They could distinguish between them. But if it is an exclusive OR sort of problem where these red dots belong to one particular type of objects, sorry, these black dots belong to one particular type of objects and the white dots the other. So in that case, the classical neural network models mostly fail because you cannot draw a single line to distinguish between them. So after these people revealed this fact, next almost 14, 15 years, there was no research, almost no research with neural networks and artificial intelligence. Classical people from control engineering and computer science thought these disciplines were dead. This was called the 1986 with the efforts of Rumelhart, Williams, and Geoffrey Hinton. This guy, he was at that time fresh graduated. His area was basically cognitive neuroscience. He was a British guy. He was a young person who started this research on multi-layered perceptron. These people developed a very fantastic algorithm for, learning of this multiple layered neural networks. And this algorithm was derived from a very simple chain rule of calculus, and it was called the backpropagation algorithm. Afterwards, this was basically the moment deep learning was born. And afterwards, the rest of the world took 20 more years, almost, until we reached almost 2010 to recognize that the multi-layer perceptrons can be wonderful, not perceptrons, these multi-layer, many-layer neural networks can actually be wonderful in learning the most suitable representation and in classifying different objects. Since 2012, to be very precise, the deep learning boom was there, thanks to Geoffrey Everest Hinton and his academic children and collaborators like Ian LeCun, Joshua Bengio, etc., Ruslan, and so on. So this area flourished. And in 2018, the Alan Turing Award was given to these three godfathers of deep learning, and the computer science community actually started to have the view that neural network is not a cargo cart science, and it became a part of basically interest for the core computer science, theoretical computer science research. That was a remarkable phenomenon, okay? So itself. Not only in images, deep learning actually had a very rich history of success, even in speech industry. Most of the speech processors in your smartphone, like Apple Siri, Microsoft Cortana, Google Now, whatever you have this in your smartphone for the speech translator, Google Assistant. Best example is Amazon's Alexa. So all these speech converters have a deep learning enabled tool in the backend to interpret the speeches. That is also basically a classification problem. Skype got a real-time translator, so you can talk to your Chinese friend. You speak in Hindi or Marathi or Gujarati, that friend speaks in Chinese, and in between your speeches will be translated into your own languages. That translation accuracy is not very bad nowadays. Okay? So cross-lingual conversation was happening in real time. This is Geoffrey Hinton once again, which was wonderful. And the research went on and on till machines could provide captions for images. Machines, actually, if you show, this is very old. I mean, this particular image is taken from a paper from CVPR 2015. 5 years means, okay, yugas in machine learning. The way things are happening nowadays, 5 years is a very long time. But at that time, the machines could provide captions to images which are better than human provided captions. Like machine writes a woman in a kitchen preparing food, which is better than and less complicated than the human provided caption. Nowadays, if you provide 3-4 related images to the machine can actually write down a story out of the images. Okay. If you provide a big text paragraph to the machine can provide you a nice paraphrase of that paragraph, nice, summary of that paragraph, and blah, blah. So these are somewhat remarkable. Deep learning that you are using every day, not during this pandemic time, but before maybe. If you were booking rooms with Airbnb, if you were ordering foods on BuzzFeed, using Google Assistant to nicely edit your pictures before uploading them in Facebook, using Pinterest for photo tagging in Facebook, group photo tags, etc. You are using deep learning. You know it or not, you are using deep learning. That's it. So it has become a part of. That's why we want to have an exposure to what it is actually. There are two deep inference models. These two distinct inference models you need to understand before you have somewhat technical exposure to it. First one is predictive model. So a predictive model is very easy. I mean, this is a traditional classifier or neural network model. Before this model, you are holding some object, and the model must tell you, after suitable rounds of training, what is this object, whether it's an apple or it's an orange or it's a dog or cat or what. So this model is more or less concerned with only placing right boundaries among representatives of different classes, so that if a new object falls to the right side of the boundary, it will belong to one class, or if to the left side of the boundary, it will belong to the other class. But then there are generative models also. What are these generative models? These are nowadays the most happening areas of deep learning. Generative models not only try to figure out those boundaries between various classes, but they also try to figure out the underlying probability distribution from where samples from a particular class might have been taken or might have been generated. So to a statistician, every object is sampled from an underlying multivariate probability distribution. If you can estimate that distribution correctly, then you become like God, because you can, sample new objects from the same distribution, which will appear as if they are from the same class. That is what exactly the generative models try to do. They try to estimate the underlying probability distribution of different classes. Once it does so, it can, on one hand, it can do the classification by correctly separating these distributions. On the other hand, it can generate many fake objects from various different classes, which will appear exactly similar to the original objects. Okay. This is good and bad both. So generative models are nowadays the most happening part of neural network. By the way, before I continue, some of you are maybe confused about the correct hierarchy of artificial intelligence, machine learning, and deep learning. Let me put it this way. These are very related fields. Artificial intelligence is the superset, the broadest field. Machine learning is a subset of artificial intelligence. It's a sub-discipline under artificial intelligence. And deep learning is the sub-discipline of machine learning. Machine learning has many more things other than deep learning. Deep learning is one of the sub-disciplines of machine learning. Around neural architectures. Deep learning, you can view it as the most advanced version of neurocomputing or neural learning systems. We usually see it in this way. Okay. So now, and the most advanced part of deep learning are the generative models, whose example is GAN. I will try to tell you briefly about GAN if time permits at the end. GAN stands for Generative Adversarial Networks. Okay. So the 2012 breakthrough in predictive learning came with this paper, which was by two students of Geoffrey Hinton and Hinton himself, imagenet classification with deep convolutional neural networks. This paper appeared in the topmost machine learning conference called Neural Information Processing Systems, or NIPS. It has, this is an old statistic. This paper has 50,000 plus citations by now. It reduced the error rate. So what is ImageNet dataset? ImageNet is actually a very large scale data set for images. It has millions of 1.5 millions to start with, 1.5 millions of tiny images collected. Images of various artifacts like coffee mug, a flying bird, dogs, cats on road, city landscapes, etc. And this database, which has 15-20 lakhs of images, had around 1,000 plus classes. So many images and so many classes. It was a terribly tough problem for the classical machine learning paradigms like random forest or support vector machines or naive Bayesian classifiers, etc., k-nearest neighbors, to tackle such a large image data set. So before ImageNet was put to a competition from the whole world, many different teams participated with their algorithms to classify ImageNet images. And the accuracy was around 70%. In 2012, Geoffrey showed that with the use of deep convolutional neural networks, once again, it's a neural architecture only. So neural networks, they can actually boost up the classification up to 84%. So the error was reduced to 16%. But this is not comparable to the human level of competence in classifying small images. What is the human level of competence? If you are shown images at rapid succession, image of a coffee mug, image of a cooking utensil, image of a dog running on the road, maybe if you are a healthy human being, maybe out of 100, 2-3 images you will mess up. All the other images you will rightly point out what are their classes. So the gross human level accuracy for ImageNet was about 97.5%. And this deep convolutional neural network, it gave us around 84%. But still, at that time in 2012, this was a breakthrough because all other machine learning systems were giving us only 70% of accuracy on gross. That's why this paper made a huge impact in the vision industry, as a result of which giant industries like at that time, Adobe, Amazon, Facebook, Google, all these giant industries towards deep learning and started investing huge money for flourishing the research in deep learning. And this network later on evolved into AlexNet, which was, Alex is the first name of this first author, Alex Krizhevsky. So the AlexNet was the, the first implementation of a pre-trained convolutional neural network in MATLAB in 2016. MATLAB is, of course, not the best tool for practicing deep learning. You need to know Keras, PyTorch, etc., Python-based platforms, because it is also free, unlike MATLAB. But anyway, this was the beginning, and this was a very heavy beginning, right? In what follows, I will provide a technical exposure to deep learning systems. Up to now, what I have talked is mostly popular science. This should be, up to this, it is understandable to most of you. Go a little bit more technical. And I acknowledge these, resources heartily. All these resources are freely available. That's the best part of it. Most of the machine learning, literature is publicly available. All the top machine learning conferences, like if I go back to the previous slide, I was talking about this Neural Information Processing Systems, NIPS conference, ML, International Conference on Machine Learning, ICCV, all these conferences release their material free of cost. You can access them if you have an internet connection. You can immediately access all these, and you can work with them. So all these resources are freely available. I will take many slides from this deep learning tutorial by Hyung Lee, NTU. Also from this book. This is the only good book written on deep learning by the fathers of generative adversarial network, like Ian Goodfellow and Joshua Bengio. This book has a nice dedicated website. You can go there and you can play around it. I mean, all the chapters are freely available. Okay. So let's have a look at it. So we start with what people already knew in 1980. Suppose we are dealing with a handwritten digit recognition problem. Handwritten digit recognition means somebody, this was the first step towards automated reading of postal PIN codes from when the US postal system was fully, digitized, computer automated. The first challenge was how to read the PIN codes and arrange letters according to the areas to which they should dispatch. So the handwritten digit recognition was there. And the basic problem was something like this. So why this? So you have a machine, you have an image like this, and the machine, which is a computer, should tell you whether it is a 2 or 3 or 4 or what. Now, how the machine does that? The input is an image like this. The machine must convert this image. Machine does not understand image. So it must convert the image into a vector like this, the plain vector of pixels. We are not going to high levels right now. So the machine must take each pixel and pack it into one of these components of these vectors, which we will call the input vector. In this case, the input vector comprises of 256 entries. So the first pixel goes here, second pixel goes there, and last pixel goes here. The output is one of the 10 numbers which should fire or which should become very high. Because we have 10 digits, 0, 1, 2, 3 up to 9. It's like the output is 10 dimensional. That means the output is like there are 10 LEDs. If the input digit is 2, then the second LED should glow, all the other LEDs should be turned off. It's like that. So each dimension of the output, we say, represents the confidence of a digit. So if the output is like this, 0.1, 0.7, the highest, and all others are very small, then we will say the number at the input is 2. Okay? So this is what common people perceive. You will give an input to the machine and the machine will tell you 2. This is what actually happens. That means the machine converts a 256 dimensional vector, because here we are dealing with 16 cross 16 only. So we have a 256 dimensional vector. The machine converts a 256 dimensional vector into a 10 dimensional vector at the output. And in terms of mathematics, we say the machine performs this mapping from R256, which is 256 dimensional real space, to R10, which is a 10 dimensional real space. This is the transformation that the machine makes. That's what we say. That's how mathematicians describe this operation. Okay. So in deep learning, this function f is represented by neural network. So if we have an elementary neuron f which maps from Rk to R, that means this, what is an elementary neuron? It's a computing unit which can map a multidimensional input to a single dimensional output. If this single dimensional output is 0 or 1, that means this single neuron is able to classify between two classes. Okay, 0 is one class, 1 is the other. Let's see how it does. This neuron accepts k many features at its input. These k numbers can be the k features which describe one object. For an iris classification system, there may be 4 inputs only, which each of the inputs may relate to the sepal length, sepal width, petal length, and petal width of an iris flower. These inputs flow through these links, and while flowing through, they get amplified or attenuated by the weights associated with each link, W1 up to WK. So then they are added with B, which is a bias term. So it becomes the final output from the summer or adder becomes Z. So this Z is basically A1W1 plus A2W2 up to AKWK, which is basically the dot product of the A vector and the W vector. And then the bias term is added with that. So this Z, if you look at it carefully, unfortunately I cannot show you with a board, but if you look at it carefully, this is for a 2-input system. Like if we are dealing only in 2-dimensional space, we have only 2 features. This would have been like W1A1 plus W2A2 plus B. Z would have become W1A1 plus W2A2 plus B. What is that? That is basically the equation of a straight line. That straight line demarcates between these 2 classes in a 2-dimensional plane. So this is what Z is. Z is playing the role of a straight line in 2 dimensions and a hyperplane in more than 2 dimensions, more than 3 dimensions. Z passes through a nonlinear element, sigma of Z. This nonlinear element could have been a, one. If Z is less than 0, sigma Z might be -1. So it actually binarizes this output Z, fixes it into one of the 2 levels. That is the ultimate purpose. But we cannot use hard limiter usually because there is a jump discontinuity in hard limiters. That's why we usually use sigmoid type nonlinearities. Anyway, so Z passes through sigma of Z and becomes the final output A. So these W1 up to WK, these are called weights. This B is called a bias. The bias actually makes your hyperplane or line away from the origin. Otherwise, they would always pass to the origin of your feature space. That is sometimes very disadvantageous. And sigma of Z is basically the activation function. A neural network is prepared by arranging such neurons. A neuron is, as I just told you, a neuron is a computing unit like this. This whole thing is a neuron. And a neural network arranges such neurons. All these circles are individual neurons. A neural network arranges these neurons in layer-wise manner. In each layer, there are so many neurons. And These neurons are connected through a feed-forward connecting system, and this way, and each of these connections have a weight associated with them. Inputs are provided to the first layer, which is also called the input layer, and outputs are sampled from the last layer, which is also called the output layer. Okay, so this feed-forward system is your neural network. Input layer, you have output layer, and in between, you have many hidden layers. These hidden layers actually are playing the representation learning. They are responsible for the representation learning. Up to 2012, nobody bothered about how many hidden layers should be there. After 2012, after the publication of the groundbreaking paper by Hinton and his students, everyone started using as many hidden layers as possible. Deep means many hidden layers. So a deep neural network is a neural network which has multiple hidden layers through which this feature information flows and gets non-linearly transformed. That creates very high-level features to describe each object. This process is yet to be fully mathematically understood, by the way. But the success is so amazing that everyone in machine learning are trying to use them. Okay? So let's see an example of a neural network, just a hand tracing example. Suppose your weights are 1 and -2, bias is 1 for one particular neuron, which has a sigmoidal nonlinearity. Your inputs are 1 and -1. I hope you can see all these numbers. If not, let me know. And your neural network comprises a sigmoid function of this sort, 1 by 1 plus e power minus z. This sigmoid function could have been centered around 0 also. So if your nonlinear element is this, when you have inputs 1 and -1 associated with weights 1 and -2, and then summed with bias 4 before you apply to the nonlinearity. So your z is 4. Now, after you pass through the nonlinearity, it becomes 0.98. Similarly, the next input is -2. After passing through the nonlinearity, it becomes 0.12. If the other bias and weights are fixed accordingly, then these 0.98 and 0.12, they become the inputs to the next layer. Okay.
Sir, your voice is not coming now. Swagatam, sir.
Hello, can you hear me now?
Swagatam, sir. Yeah. No, yeah. Now we can hear you.
Suddenly it became muted anyway.
Okay.
So the 0.98 and 0.12, these outputs from this first layer become input to the second layer, and they are processed in the second layer. And as a result of that, after passing similarly through the second layer, it becomes 0.86 and 0.11. These are the inputs to the third layer. After passing through the third layer, it becomes 0.62 and 0.83. So this is how it. So if the inputs would have been 0 and 0, then the outputs would have been 0.51 and 0.85. So this, we say this neural network is mapping from R2 to R2, first of all. We say it takes 1 and -1 at the input and gives 0.62 and 0.83. It takes 0 and 0 and gives 0.51 and 0.85. Now, who determines this? Who determines for given input what will be the output? This is determined by these weights and the biases. So we need to, fix the weights and fix the biases. This is very, very important. So what are these weights? These weights are basically when if you are familiar with communication links, when a signal flows through a communication link, which can be where even, while passing through the link actually either reinforces or strengthens the signal or weakens the signal. Weights are also like that. weights are like gates, which if fully open, they can reinforce the signal, the feature value. That means if a weight is greater than 1 and that weight multiplies one particular feature value, then the feature value will be amplified, will be more than previous. But if the weight is less than 1, very small number, and it multiplies the feature value, that means it is suppressing the feature value. So at the input, we are giving all the possible low-level feature values. Then those low-level feature values are flowing through the network. While flowing through the network, these feature values are being attacked by various weights. If the network knows exactly the optimal weights, which they initially do not know, but if they know the right and optimal weights, they can actually reduce or suppress the unnecessary features and reinforce or amplify the most contextual features. Then they can actually non-linearly combine these features to have high-level descriptions of each object. That is the role of the weights, basically. Okay, they are controlling how the features, low-level features, should be flowing through the network and combining in later stages to generate most contextual high-level features. Anyway, so now different parameters. So what are the parameters of a neural network? These weights and biases are the parameters of the neural network, and different parameters actually define different functionalities of the network. We can describe them in terms of matrix operations. If some of you are from electrical engineering background or are familiar with state space representation, it's very good for them. So we can pack up all the weights into a weight matrix like this: 1, -2, -1, and 1. We multiply 1 and -1, the inputs, with this weight matrix, and we add the bias vector 1 and 0 with this vector matrix product. This gives us 4 and -2. We pass the whole thing through the sigmoid nonlinearity to get 0.98 and 0.12. This is a very smart way of writing the neural network operation. Okay. So now, as you see, for each layer, we can specify a weight matrix W and a bias vector B, and the input is, suppose, X. So this becomes Wx plus B. So now I can represent my neural network in terms of weight matrix and bias vector for each layer: W1, B1, W2, B2, dot, dot, up to WL, BL for each layer. Okay. And then suppose X is your input. When X passes through the first layer, it becomes sigmoid of W1X plus B1. That forms the output to from the first layer. Let's call it A1. So the same A1 is the input to the next layer. Okay. After it passes through the next layer, it is processed in exactly similar way. So it becomes C. So this is A2. What is A2? A2 is the processed version of A1. Okay. So A2 is the processed, and it becomes this W2A1 plus B2. This is basically passing through the sigmoid nonlinearity, and it becomes A2. This way, after it passes through all these layers, it becomes Y, which is the output. So how this Y, the output from this neural network, is related to its input? We say Y equal to Fx. If you remember, I began my lecture with this simple mathematical representation. But inside this function Fx, there is a hell lot of complications. Actually, this function Fx is a very highly nonlinear representation of the input X. So we say X is here. It passes through the first layer, it becomes plus B1. Then it passes through the next layer, it becomes sigmoid of W2 times the previous A1 plus B2. This way, after passing through L many layers, it becomes a very highly nonlinear representation of the input. Such higher degree of nonlinearity gives us proper feature selection and describe objects in a more abstract manner. And this is a very nice, mathematical representation of the neural architectures. Usually, at the output, when we are dealing with a multi-class classification problem, when we have multiple output classes, usually at the output, we provide a softmax operator. What is this softmax operator? It converts the outputs into proportionate probabilities. So if the actual original outputs would have been Z1, Z2, and Z3, so when they are passing through the sigmoid layers, they are becoming Y1, Y2, and Y3. These Y1, Y2, and Y3 can have any different values. And they are sometimes not easily interpretable. Their physical units may change. You don't know what is their, if they are physical quantities, what are their units? You may not know that. That is why what we do in the softmax layer is, if the original outputs are Z1, Z2, Z3, we convert them to e to the power Z1, e to the power Z2, etc. Then we add them into the sum. Then we divide each individual exponential by this sum, so that ultimately the final outputs become Y1, Y2, Y3, sum of which is always 1, each of which lies between 0 and 1, and therefore these Y1, Y2, etc. can be interpreted as probabilities, discrete probabilities. I think you all know that. So when Y1, Y2, Y, so if Y2 is, suppose Y2 is 0.9, Y1 is 0.05, and Y3 is 0.05. What does that mean? That has a very straightforward interpretation, that the input object belongs to the second class. There are 3 classes designated by 3 outputs, and the input object belongs to the second class because Y2 is maximum. If Y1 would have been maximum, we would say the input object belongs to the first class, and so on, right? So this is a numerical example, 3, 1, and minus 3, it becomes 20, 2.7, and 0.05 when you exponentiate them. That means you take their exponentials. Then when you sum them up, they become simply 0.88, 0.12, and almost 0, because they're a very small number. Usually, the output of the neural network always passes through a softmax layer. Therefore, outputs are represented finally in terms of the proportionate probabilities. Now the question is, how to set the network parameters? How do we know the right network parameters? Suppose theta is the vector comprising of all weights and biases, W's and B's. Now, how to set the network parameters theta such that when the input is something like this, in we are dealing with the handwritten digit recognition problem. This is the example with which we started. So when we give this input, the Y1 will have maximum value because we are dealing with softmax. Y1 should have maximum value. When we give this input, Y2 should have maximal value, etc. How to achieve that? To achieve this, I told you from the first 1-2 slides in my lecture that in supervised learning, the machine has to be given with some experience. Experience is given to the machine in the form of training data. What is training data? It's a set of labeled examples, labeled sample classes. Who labels them? Experts. For some classification tasks, such human expertise is very costly. For some classification tasks, such human expertise is very cheap. This digital handwritten digit recognition is an example where the labeling is very cheap because all of us know how to write 1, 2, 3, etc. Right? So you will ask 10 of your friends, 20 of your friends to write from 0 to 9. You will cut their handwritten digits into small pictures. and provide to your computer, or you will take a mobile phone snapshot of these pictures and provide to your computer. Then you will have 20 such labeled samples from each classes. And you will have a training set of size 200, 20 samples from each classes. This doesn't require expertise. But if I want to distinguish between, say, lung CT images, okay, whether the person has lung cancer or the person is benign, then that labeled set must have the expertise of an oncologist, a doctor who may charge $2,000 per, per hour. That expertise is very costly. So training data, preparation of the training data is the phase where the teacher enters into the picture and the teacher provides you with experience. Okay. After this training data is prepared, now what is the next step? Now we define a cost. What is this cost? Initially, we start with the neural network all random valued parameter. We do not know what are the correct weights and what are the correct biases. So we start with all, random weights and random biases. Then we pick up our first training data. For this training data, since we already know it is 1, for this training data, the target output should have been 1 and all zeros. But the neural network gives you something like 0.2, 0.3, all these meaningless values. This is very, very simple. You are asking a student about a question which the student has not learned. So the student will give you all the answers. Same thing is happening with the neural network as well. Initially, it is not trained. That is why it is giving you a haphazard answer. Now you want to measure how much wrong the neural network is committing. You want to measure that by, looking at how much different these two things are, how much different the output from the neural network is from the actual desired output, and you measure it in terms of the cost. This cost could be a simple Euclidean distance actual output. Okay, call it L theta. So for each training data, you prepare L1 theta, L2 theta, L3 theta, etc. up to LR theta. So your total cost, the sum of all the individual costs on individual training data. Now, so basically what you are doing, suppose you have 200 training examples on each, how much error the neural network is making from the right answer. So you take this difference between the actual response and the desired response somehow into this L1 theta, L2 theta, L3 theta, etc. And you term the total summed error as C theta, which is a function of course, the parameters of your neural network. Now you want to determine such a theta for which is least. So your entire endeavor boils down to an optimization problem. You want to find such a theta for which you want to find a theta star for which this C theta becomes minimal. This is where the optimization thing comes up. So this optimization actually fixes up all the weights and biases of your neural network. And traditionally, it is done by using the famous gradient descent algorithm. Let's have just a very quick review of that. Gradient descent is very contextual for neural networks as well. These are used inside the backpropagation learning algorithm. Suppose you are representing you have only two parameters, W1 and W2, and your cost is, so your theta is simply W1, W2, this vector, and your cost function surfaces are elliptical, which are shown here with various ellipses. So these ellipses have some values marked on them, which are the values of your cost function. Now, what you do is you start with the colors represent the various values of C, and you're optimized somewhere near 0 and 0. So your optima is here. You start with an initial starting value of W1 and W2, which may be random. So you start with this theta 0. Now you compute the negative gradient of the cost function C at theta 0. By negative gradient, we mean a vector comprising of the partial derivatives of C with respect to W1 and W2. Then you go along the negative direction of the vector. So you take minus of grad C at theta 0, and you take a jump along this direction of magnitude eta. Actually, these gradient vectors are always perpendicular to these ellipses along which the value of C remains constant. These ellipses are also called constant cost contours or isocontours, and the gradients are always perpendicular to the isocontours. So you take a jump along this negative gradient direction. So you appear here, then you take another jump, you appear here. This way you go along the negative gradient direction until, if you are lucky enough, you will reach a very good optima, which is in this case the center of your weight space. But gradient descent never guarantees global minimum. Sometimes, most often in deep neural networks, your cost functional surface is having multiple minima and maxima. We call such surfaces non-convex surface, and the gradient descent will lead you to the nearest minimum, because as soon as you reach the minimum, the gradient vector will vanish. So you have no other direction to jump. So as a result of this, you can start jumping with various different theta zeros so that you can reach more than one minima each time and then select between them. There are various variants of gradient descent, but gradient descent is not scalable. If you simply, your cost function comes as in terms of sum of individual losses on individual training examples, like Hx is a sum of f of x given yi. This f of x given yi is basically the individual loss on each training example, and your gradient descent is a sum of such individual losses. Since the derivative operation is linear, so gradient descent is also linear, and if there are capital N training examples, your gradient calculation will take order of capital N time. So when you are dealing with a large scale data like imagenet, where you may have 1 million training examples, 10 lakh training examples, or more than that, millions and millions of training examples. In such situations, the each gradient update step will take huge amount of time. To get rid of that, we have two versions. One is mini batch. That means you can break up your training set into small batches. This is one core technique for training deep neural networks only. The mini batch gradient descent, where you actually break up your training set into small batches, randomly pick up some theta 0, that means randomly pick up the initial values of weights and biases, then pick the first batch. So if you have 1,000 training examples and you are breaking them into 100 batches, each batch contains 10 randomly selected training examples in a mutually exclusive manner. So suppose your first batch contains training example 1, training example 31, and so on. So the cost function for the first batch is L1 plus L31 plus ... so on. You update your weights on the basis of the gradient computed on the first batch. So you go from theta 0 to theta 1 following the standard gradient descent equation. Pick up the second batch. Second batch contains L2, L16, etc. So you update your theta 2. The next updation of your weight and biases will be done on the basis of the total training error computed on the second batch only. So remember, every time your C is different, but still this method converges. There are mathematical theories in support of that. This is faster, and this is done until all mini batches have been picked. Even then, if the weight values are not converging, convergence to a minimum means the gradient magnitude should become very small. Even then, if it doesn't happen, then we again break the training data into small batches and repeat the same procedure, faster and better. Very interestingly, before I start drawing conclusions, very interestingly, The state-of-the-art methods for training deep neural networks are all based on stochastic gradient descent. So in stochastic gradient descent, what we do is, this is just a special case of mini batch gradient descent with batch size 1. What we do is we randomly pick up a training example. We calculate the error the neural network makes on the training example. That is called output error or loss. We can compute the loss as cross entropy loss or Euclidean loss. There are a variety of losses, and 1-2 hour lecture can again be given on losses. So I'm not going into that specific topic. So we calculate the loss, output loss or output error for a single training example, and we immediately update our weight vector based on the single loss. Okay, this is a special case of mini batch gradient descent. So once we update, then we again randomly pick up another vector, another training component, and perform this output error calculation. Then we again update based on that single loss only. So instead of adding the losses over variety of training data, we just pick up each example, one randomly sampled example, calculate the loss on that only, and update our training parameter, our neural network parameters. Very interestingly, this method was proposed in 1951. Most of us were not born at the time. So in 1951, and the rest of the world took so many years to understand that this could be the tool for training neural networks which we are using in 2020. This is a classic example of delayed recognition. Okay, so now I will go to, in fact, another set of slides to make things more appropriate, and I will reshare my screen just in 1 minute or so.
Sure, sir, sure.
Yeah, so I will start from here. The concluding part I will mostly start from here.
Sure, sir, sure.
So as I told you, structured learning, deep learning gives us a specific example of structured learning, And the structured learning is, the whole job is to find a function f which maps from one input domain of x to the range y. Every function, you probably, if you recapitulate your 10+2 calculus course, every function has a range and a domain. So deep learning is about finding the suitable functions from one specific domain to another specific range. For example, in case of regression, the output is a scalar number. In case of, and different tasks have different names. Classification, the output is a class, may be represented as a one hot vector. So class 1 is like this, class 2 is like this, class 3 is like this, etc. Structured learning output can be a sequence or matrix or graph or tree. Classification and regression belong to the classical machine learning. On the other hand, deep learning is mostly concerned about structured learning or prediction. So, for example, in case of machine translation, X can be a sentence written in Chinese and Y can be the sentence written in English. So when we map from X to Y by using a function, this function is our deep learning system, okay, which provides an English sentence for a Chinese sentence. Speech recognition, X can be a speech signal which may be recorded with your computer, and Y can be the corresponding transcription in some language, maybe Chinese or maybe English or something. Chatbot, X can be some sentence which the user types. Y can be the corresponding response from the machine. Okay. The output is a sequence, the input is a sequence. Similarly, the output can be a matrix, like input can be an image like this, input can be a sketched image. Nowadays, the deep learning systems are like that. And the output can simply be some kind of, actual image generated on the basis of the text image, on the basis of the hand-drawn image. colorization. The input may be a set of bottles. The output may be the colorized set of bottles. Many, vintage movies are being represented in colored form like this. Similarly, we may have text to image. Now, this is the most advanced type of deep learning. Input is text, the output is round yellow stamen. This is the description, and the neural network generates image of this sort. That neural network gives you some images like this. These are the examples of structured learning. So I will skip through some of these slides. Okay. So this is the difference, as much as I have explained, this is the difference. The 1980s era neural networks used to have only one single hidden layer. Now we have multiple hidden layers. I told you how the information actually flows through the multiple hidden layers. And these hidden layers, in case of image recognition type of task, what they do is they actually combine different low-level features like the pixels, object parts, nose, say the eye opening, eyebrow constriction, lips, etc. And finally, for these are applicable obviously for the face database. There are multitude of other applications where the low-level pixels are combined into different high-level parts of the image. And finally, these high-level descriptions help us to correctly classify the images. So these are deep neural networks of next generation. Okay? How it goes. So as I told, used imagenet for classification. Shallow neural network models with 25.8% error rate. Error rate is 100 minus accuracy. 28.2% error rate.
Sir, your voice is not available now. Swagatam, sir. Sir, are you there? Yeah, dear participants, please wait for a minute. I think he has some network issue. He'll be joining once again. Please wait for a minute.
Hello.
Yeah. Yes, sir. Yes, sir. I think there
How
was some
the
network
connection
issue.
went off. I
Yeah.
don't know.
Yeah, it's okay, sir.
So
No
let
worries.
me reshare my screen once again. I don't
Sure,
know
sir. Sure.
where I was. So probably here. So as I was telling you, the revolution of depth. If you look at this AlexNet, which was the winner of the ILS-VRC 2012 competition. ILS-VRC is the name of the competition in which AlexNet was used for classification of imagenet dataset. Its full form is Visual Recognition Challenge by using imagenet, large scale visual recognition challenge, LSVRC. It's still on. So AlexNet had only 8 layers. Then as the number of layers were increasing, the accuracy also increasing in subsequent years. For example, ILS-VRC 2014 was won by GoogleNet. This is a specific deep learning architecture which was prepared by Google company, and it had 22 layers, hidden layers. Finally, in 2015, the residual network, this is also ResNet is the name given to the very state-of-the-art deep neural network structure, which won the AlexNet competition, which won the ImageNet competition. It had, as you can see, 152 hidden layers. So number of hidden layers increasing. What does that mean? It means huge number of parameters, huge number of weights and biases have to be trained. This requires a computational hardware of huge scale. So that is why usually the deep learning nowadays, after this 2015, we have passed by 5 years. Now we use ResNet, ResNext, PCANet, DenseNet type of neural architectures, which cannot actually be trained by using a simple laptop. That is why if you want to carry out some meaningful research on and with deep neural networks, you have to switch to GPUs, graphics processing units. Usually NVIDIA manufactures all the GPU. The GPU market is entirely under NVIDIA. Or you have to hire some cloud computing facilities under Google, G Cloud or something like that. This is one problem with deep neural networks, that still the hardware support cannot be obtained from a simple laptop. Although we have very good optimizing algorithms by now, so the training time has reduced by a large extent. For example, previously, this AlexNet in 2012, it would take 1 month, 30 days to train the whole imagenet data. You start the program, after 1 month, you expect it to be trained. Now, training on imagenet with a good GPU has come down to 40 minutes to 1 hour time. But still it cannot be done with a simple, laptop. So convolutional neural networks, what it does is, this is just before I end up, convolutional nets take an image, it actually compresses the image by just picking up the most distinguishing features. Like if you want to, segregate birds from non, don't want to look at anything else. If it is a bird's image, there should be a pointed beak here. So you may want to slide some kind of, feature detector, which when it gets a beak like this, records a huge response. Otherwise, it won't do anything. So convolutional neural network passes various feature detectors on the image, prepares their responses, finally in the form of a vector like this, and these vectors are provided to the fully connected neural architectures, which then does the classification. So convolutional neural networks actually compresses an image into a small dimensional feature vector, which is finally used for classification. Nowadays, if you have a 9 megapixel camera, that means not 9, suppose you have a 3 megapixel camera. So you are taking a picture which has 3000 pixels along the width and 3000 pixels maybe along the length. So it can have, 9 megapixel camera means you have 3000 pixels along the length and 3000 pixels along the width. So that makes your total number of pixels 9 million. So these 9 million pixels, if you want to process 9 million pixels together, that can be fairly bad. So you have to pack it into a vector of 9 million dimensions. No computer is going to support you. Convolutional neural network actually summarizes the best features of the image into small, it summarizes these main features into only 5,000, 6,000 numbers, which can be arranged into a fully connected vector and can be subsequently used for classification. This is what the convolutional neural network does. And finally, generative adversarial networks, which is the most interesting thing. And as you can see, this network was, provided in 2014. It was proposed by Ian Goodfellow, who was a PhD student under Yoshua Bengio. They are all from University of Montreal, Canada. They are not from US even. So this work attracted huge attention since 2014. What they do is, if you show, GAN is a neural network to which if you show images of a particular kind, GAN can generate similar images by estimating the underlying probability distribution. So when GAN was trained with portraits drawn by medieval period artists. GAN drew this portrait image by its own self. And it was auctioned in US in 2018. Somebody was ready to buy it for US dollar 4,32,500. So it is so realistic. So there is a signature here below the image, just like artists sign their names below their images, and the signature reads Generative Adversarial Network. So GANs are very good at generating fake images by using the mathematical principle of underlying the probability, approximating the underlying probability distribution. GAN usually has two neural networks. One is called discriminator and one is called generator. The generator picks up random noise vectors and converts those noise vectors into generated images. On the other hand, you have a collection of real images of some specific type, like images of faces or images of bedrooms, images of bottles, something like that. The discriminator is there, which determines whether the image shown to it is a artificial image or a real image. So the discriminator tries to distinguish fake images from real images. Discriminator is a classifier neural network. Generator is usually a neural network with reverse flow, just like convolution, deconvolutional network. A reverse flowing neural network which generates input images from output vectors. Sorry, which actually generates images from vectors. It picks up some vectors from random noise and gradually modifies those vectors into images. These images, it must learn generating images which look as realistic as possible. So these two neural networks compete with each other. They are like police and thief. The thief tries to manufacture fake currency. The police tries to capture and distinguish the fake currency from the real currency. This way, both actually, improve. And its stage comes when the police, if the GAN becomes successful, it can reach a stage when the generator is doing really good and the discriminator is not able to tell whether the image is real or fake. Anyway, I don't have enough time to speak up on all these intricacies. Let me show you some results instead. For example, these are the samples generated by GAN from various object classes, like horses. These horses were never born. Sofa sets which were never manufactured. Buses which never were on the earth, etc. How the GAN images evolved with time. You see, in 2014, the image quality was very bad. 2017, 2018, we have almost photorealistic quality of images. And these images are generated by neural networks. This person whom you can see in this 2017 tag, he does not exist. There is nobody like him. It's a fake image which looks very photorealistic. So these are also various artifacts and images generated by GAN. Now there is a GAN paper almost every week. I will almost conclude the proceedings by showing some very interesting future research issues. Let me skip through the images, slides a little bit. Okay. Yeah. So first, one very big problem during my concluding remarks would be, deep neural networks are not magical. They require huge amount of training data. Even GANs also does the same thing. Plus, deep neural networks have huge number of hyperparameters. Like hyperparameters are like how many hidden layers are optimal for a particular classification. Somebody says 150. Why not 120? Why not 200, etc. So how many nodes must be there per hidden layer? I mean, how many neurons there should be per hidden layer? What should be the activation function? Should it be sigmoidal, or should it be ReLU, rectified linear unit, which is nowadays most often used? Should it be leaky ReLU, or should it be hard limiter? What it should be? So there are multiple such questions which cannot be answered only through trial and error. That is why nowadays people started to follow the principles of Darwinian evolution. Evolution is the mechanism in biology which were responsible for fine-tuning the brains of human beings, starting from the age of Neanderthal people. So over millions of years, our human brains have evolved. That's why we have become so, clever. and smart these days, can we use the principles of neural evolution to fix up the hyperparameters and other things, other intricacies of a neural network? That is one very interesting future research issue. Uber, Google, and Facebook are investing lots of dollars behind this research. For example, can we evolve the generator of a GAN to come up with very realistic images right now? Similarly, can we protect our neural networks against adversarial attacks? So you see this panda image, when it is added with slight noise, sometimes the CNN can do very funny things. Convolutional neural networks was calling it a panda with more than 50% confidence. As soon as you add some noise with it, convolutional neural network calls it a gibbon with 99% confidence. This is a very big problem, because to a human visual system is so robust that if you look at these two images, you still know it as a panda. There is no visual change. So this is one thing. And also, if your high-level features are misaligned, for example, you have a pair of lips at the forehead, still CNN will call it as a face. As a remedy to this, more new generation neural architectures are coming, like Hinton's capsule networks and so on. More tool applications are being developed, like we have this neural photo editor. We can generate any street scene from labels. We can generate a sketch from an input image, or a realistic output from a sketch. Can we do such research more and more? Nowadays, I mean, this is I don't know whether you can look at it or not, but this shows how you can bring back older paintings into life. This shows Mona Lisa, in the famous Mona Lisa painting, in 3 input expressions. So you give some input expression and you can actually, export that expression on some old painting or old artifact, bringing them back to life. So one person's expression can be provided into another person's expression. Movie industry has a huge stakeholding on it. So this is how the actual shooting is done. So this person sits on a rock, and when he's transformed by using computer graphics, he looks like this. So this is how the movie is being shot. A person in this green attire holds the dummy of a dog's head, and it looks so realistic in reals. Nowadays, movie industry is one of the biggest stakeholders of deep learning. Similarly, medical imaging and other serious imaging industry, especially astronomical image analysis, they are holding big stakes of deep learning. This is the last slide where I show Geoffrey Hinton, who is the father of deep learning. He still believes that whatever he says, whatever they have invented, is light years away from how the human brain actually functions. Human brain is really remarkable, and its actual functionality is still beyond our understanding. So he says the future depends on some graduate student who is deeply suspicious of everything I have said. That's why keep on doubting. Probably from those doubts, new questions and new future research avenues may be unearthed very soon. So thank you very much. With this, I would like to conclude, and I can take a few questions if there are some.
First of all, hats off to you, sir. You have been so clear throughout your presentation that by the participants, this session has been rated so far the best session of this FDP. So I would like to congratulate you for that. And you have touched upon every nook and corner of this subject. You have not left any, I don't think that you have left any question unanswered. I hope that most of the questions have already been answered during your presentation. And you have been parallel to Andrew and Ian, this fellow, I can say, while discussing this presentation. So with this, we have now 2 modes, sir. In your particular case, if you want to, if you can look at chat section, then you can pick up the question on your own, because but I think that most of the questions are already answered. I don't see any space there that there is
I
any
think
need to answer any question.
I take up 1-2 questions from the chat
Yes, sir.
session.
That will be better.
Discuss. For example, some of you wanted to know what is meant by what is the need of bias. Okay, so this bias term B, which was there, if you think of equation of a straight line, what is the equation of a straight line in 2 dimensions? Suppose if I say only y equal to mx or ax plus by equal to 0, that is a straight line passing through the origin always, right? Do you know that? I mean, y equal to mx is the straight line which passes through the origin always. But if you represent the same straight line as y equal to mx plus c, there is a constant c. This constant is same as the bias in our situation. This constant shifts the straight line from the origin. Origin means the point at which all features must become 0 in your feature space. The bias vector actually gives us the flexibility to shift the, the hyperplane, which is there to distinguish between 2 classes, one class on this side, one class on that side, and you have a plane in between. So you can put this plane anywhere. It need not pass through the origin of the feature space. That is the basic idea. That is why bias is used. Okay, and as I told you, weights are used for suppressing unnecessary features and amplifying the most important and most contextual features. Okay, there is a question here that is it possible to execute deep learning model inside smartphones? Let me tell you, in deep learning, the most time consuming part is basically the training. If your neural network is trained, already trained, that means your neural network has already all the weights and biases, all the weights and biases are already adjusted. Then that pre-trained neural network can recognize any unseen object or artifact very quickly. That doesn't need time. Usually our smartphones have systems like this, all these Google Assistant. When you install an app that contains a a realistic photo editor or a photo tagger or some other kind of like converting maps into areas or maybe imposing realistic photo finishing effects on Google satellite images, all these tools have pre-trained neural networks behind them. So there is no point in, I mean, if you cannot train a neural network with your smartphone, but you can obviously use a pre-trained neural network with your smartphone only. That doesn't take time. Okay. There is another question. So yes, it is possible very much. Many apps actually use that principle. Is NLP algorithms always work behind AI? NLP is, and let me tell you, artificial intelligence is a very big area. Natural language processing is also a subset of artificial intelligence. NLP has big overlaps with machine learning, and of course in deep learning. There are special deep learning architectures dedicated towards NLP, which only deal with NLP, and these are very basically the recurrent neural network architectures. The recurrent neural network architectures, like we have various types of, what I have talked is basically the feed forward flow. These architectures also have the feedback loops inside. They can actually process sequences of texts, and they are dedicated towards NLP. But convolutional and other computer vision neural networks may be different from NLP. As days are going and things are becoming more and more improved, the distinction between NLP and computer vision is actually fading out. Nowadays, as I told you in an example, you can type a text description, 2-3 lines of text, and the computer neural network can draw an image which matches with your text. So this is a perfect example of interaction between NLP and computer vision. Okay, so there is a very pertinent question just now. Do you think there will be a problem to security because of AI? This is a very important question. See, first of all, now there is a big research paradigm which is called privacy preserving deep learning. privacy preserving machine learning, where the training data, the whole of the training data may not be exposed to the deep learning system. Or even if the training data is provided to the deep learning system, there will be certain cryptographic protocols which must be maintained so that from the deep learning system, a third party may not extract the training information or may not hack the training database. These are under the privacy preserving learning paradigm. Privacy preserving learning, if you do the Google search, you will get many, various, websites and research agenda on that. This is very important. I can share some of it with you also. And another very interesting thing is this GAN, as I was telling, it can generate many fake images and fake texts, etc. It can actually write a story for you. It is always like a two-edged sword. You can use it for good purpose and bad purpose. Somebody can generate a fake news which can create hatred and just trigger up a riot by using GAN. GAN can be used to generate, fake riot situations in various parts of the world, and usually there are various groups in Twitter and Facebook which regularly does that, which should not be done. That is why in medical imaging, when we are using GAN for generating artificial samples, we have to be very cautious. In medical imaging, somebody can generate artificial medical reports showing tumors in your chest CT image or other kind of internal organ images, which can be dangerous, which is an alarming false positive situation. So that is why nowadays ethics has become an important part of artificial intelligence education. Practitioners of artificial intelligence must have a very important sense of ethics. Okay, that's why AI and ethics has become a good subject right now. Every such tool is a two-edged sword. You can use it for good and bad purpose. It's up to you how will you use it. So there are many other questions, I think, but I have to. For example, can we solve combinatorial optimization problem using machine learning? Usually, no. Combinatorial optimization problems, some neural networks are there for solving traveling salesperson type of problems. These are called chaotic neural networks. But usually, the results are not that good. For combinatorial problems, we still prefer theoretical computer science type algorithms. But there are also situations where you cannot do them, where exponential runtime is there. I think more at present, I do not see any such well-defined research paradigm, but this is a very, very important and open research area. If you can solve an intractable combinatorial optimization problem with deep learning or similar neural architecture, you will become very famous person overnight. So it's a very open problem. And thanks for raising this problem. Then there is another, is it feasible to apply fuzzy logic to, of course. I mean, uncertainty modeling, many of the training data may have huge degree of uncertainty associated with it. When we are, for example, when we are dealing with, there are nowadays deep learning systems which can demarcate between fake news and real news. Now, real news, from which source that news, that tweet or that text or that video is coming, based on that, you can give a fuzzy degree of reliance to each of your news items. Okay. See, the training data may be sampled from different sources. Different sources may have an associated fuzzy membership of their belief, how realistic they are. Also, fuzzy belief may be associated with your activation function itself. There are various implementation of fuzzy deep neural network. Fuzzy sets are there for quantifying the uncertainty associated with training data, quantifying the uncertainty associated with optimization of your weights, and in various other stages. So fuzzy deep neural networks are also very good resources. Okay. So there is a question referencing to the example of Chihuahua and Muffin. How do we decide with which object feature we should match the features? See, deep neural networks can do that without any human intervention. And still date, we do not know exactly mathematically how it does. But for us, for human beings, when you look at these images, you immediately grasp that the two eyes and the nose for the Chihuahua puppies are almost arranged in the form of corners of a uniform triangle, okay, equilateral triangle. But for the other case, I mean, for the Muffin, the cherries on the muffin may not be arranged in that manner. They are more irregular. So that feature is one of the most indicating feature that this is a chihuahua with cherries on it, and this is a regular, this is a chihuahua with this eyes and nose, and this is a muffin with cherries on it, right? So these are the some of the very distinguishing factors. What is activation function and how it is decided? Activation function is basically the decision maker. So when you have, say for example, if you have your Z as A1 W1 plus A2 W2 plus B, this is the equation of a line. Now you have some points on this side of your line and some points on that side of your line. If you plug in the coordinates of a point from this side into the line, it becomes positive. If you plug in the coordinates of a point from that side of your line, the equation of the line becomes negative. Okay. Now the activation function simply extracts the sign of this line. If it is positive, the activation function gives a very high value. If it is negative, the activation function gives you a very low value. So it kind of, binarizes the decision and puts you into one of the two possible classes in a binary neuron. For multilayer neurons, of course, the activation function or the softmax values puts you into one of the 5, 6, 10 possible classes. That is the main idea of it. Okay. Can an intelligent or trained machine recognize duplicate emotions of any human? This is a very subjective question. Till now, emotion recognition is a problem, but we always assume the emotion is real. If you are very angry about some guy, you want to kill him, but you poses a very smiling face to that person, and the computer is there to recognize your emotion, it will recognize you in a very happy mood. Okay, it cannot enter. Unfortunately, machines cannot enter, cannot read your mind. I hope maybe 50 years from now, we will be discussing on this mind thought reading machines. So with this, I would like to conclude. I have some other important meetings pending. Thank you very much. Any other question? I have my email ID with Professor Ankur Choudhury knows that.
Yes.
You can
Yes,
share.
sir. I have.
Happy to answer many other questions offline. Okay.
Thank you so much, sir. Hats off to you once again, sir. And as you can see in the chat section, how many appreciation messages are there in the chat section. But one common question is still there, and people are very much interested in getting the slides. Is it possible to share the slides?
Yeah, of course, I can share the slides, but you share it only among the participants. Don't put it in any public repository.
Definitely, sir, definitely. And one more thing, sir, we will also share the feedback given by the participants in the form of a photograph. We are doing that also. So we will send you the feedbacks in a portrait shape with the certificate of appreciation, sir.
Thank you very much. So
thank you for accepting our invitation, sir.
As an email, Professor Ankur, I will send you the slides through an email.
Yes, sir. Okay. Sure, sir. Sure. Thank you so much, sir.
Thank you so much, sir.
Thank you, sir. Thank you.
So one more thing, sir. One more thing.
Yes, yes.
Can we ever plan a session on soft computing or evolutionary computing, as you are also an expert of that area?
Yeah, of course. You can plan the session. Let me know the timing. I will adjust it.
Yeah, thank you so much.
Thank you so much.
Okay.
Nice of you, sir.
There is a poll again on the session.
Dear participants, we are going to just throw a poll. It will not take more than 30 seconds.
No, it will take right now. It will take 1 to 2 minutes.
भेजा भी था, अनमोल रतन पे भी भेजा था और पीएससी वाले भी भेजा था। 200 रुपए का तो
लगाएगा तो बात आपको यही आती है किसी ना किसी
Statements correctly represent a neuron has a single input and a single output.
देखना बहुत इंटरेस्टिंग टॉपिक है।
A neuron has multiple inputs but a single
How was the session?
शुरू से
has a single input but multiple
मेरी बलाते कोई लगाओ
She will involve her.
तो नाम है
neuron has a
This
single
girl is
input
a
and
junior
multiple
girl. She do all the things for her, like Sonia. Yeah. The whole work is done by the Srividya only, ma'am. The whole thing. Everything she does.
शुरू से समझाते हैं और एकदम
उनसे फिर से पूछना।
क्या बोलते हैं उसको,
अबे वो बताइए यार
सिंपल वर्ड्स, ऐसा नहीं
neuron
How was
network
the session?
various
आइडिया होना है पहले।
or transformation or scaling an input in the statement correct, true or false.
हाँ यार अब तो होगी, अब तो खुलेगा सोच के ना, मतलब लग रहा है।
बता दो एवरीवन अनम्यूट मोड। मैंने ये बंद कर दिया था।